Thank you so much for the introduction. My name is Zaiqing. I'm a senior scientist at VTT, Technical Research Center of Finland. I would like to acknowledge my student Aleks and my colleague Tommi for their contributions. So as the chairman mentioned, that I will talk about the effects of pressurized water reactor environment, also the cyclic loading parameters on the low cycle fatigue behavior. Austenitic stainless steels, they are widely used in light water reactors due to their accident general corrosion resistance. However, they can be susceptible to environmentally assisted fatigue due to the non-monotonic loading conditions in operation of the nuclear power plants. And this is mostly linked to the low follow modes during operation. And there are quite often small changes and plant shutdowns and startups during the operation. And EU in Sapphire scale is a 5-year European Horizon 2020 collaborative project. The project aims to develop an improved understanding on the effects of environments, loading spectrum, strain rates, and temperature on the low cycle fatigue behavior of austenitic stainless steels. The material we used in this project was fabricated in France according to the RCCM standard. It was fully solution annealed equi-etched stainless steel 316L. We have both solid bar specimens and hollow specimens, and they were fine polished on the surface, and the polish marks were having a 45 degrees angle to the loading axis of the specimens. And the final polishing was done with a slurry paste, which results in a very limited deformation under the surface after the machining. And this final finish results in a very limited, very small roughness, which is roughly 0.18 micron for the surface. In addition to the FCC matrix, we have delta ferrite presence in the materials. They are mostly elongated in the loading directions, and then they have higher chromium and molybdenum contents, but lower iron and nickel contents compared to the FCC matrix. At the interface to the matrix, they have high angle grain boundaries, and in the segments, they have low angle grain boundaries between the delta ferrites. And there are two kinds of inclusions present in these materials. The first kind is the oxides. They are enriched in chromium, manganese, and titanium. And the second type is the manganese sulfates. ASTM standards for low cycle fatigue testing were followed during the tests. The tests were performed under direct total strain controls. The fatigue life criteria was the N25, which is the cycle number where there was a 25% of the load drop. And for the hollow specimens, the failure was defined as a stool failure or leaking of the hollow specimens, and this value is commonly assumed to be equivalent to N25. In the Sapphire scale projects, we have 3 testing phases. In phase 1, we have 88 valid low cycle fatigue tests. And of these 88 valid specimens, we performed detailed catalyzation of 25 specimens. And in this presentation, I will present the results of A representative specimens. This table shows the tests we performed in high temperature air and then in the high temperature pressurized water reactor environments. In the simulated pressurized water reactor environments, we have a testing temperature of 300 C under pressure of 150 bar. And then we have 2 ppm lithium, 1000 ppm boron, and then 25 cc of hydrogen, which is identical to the environment normally used in pressurized water reactor. The loading used for the programs has 2 types of waveform. The type 1 is a constant amplitude, so which is the common sawtooth or triangle waveform. And then the second type is the varying amplitude, and which consists of either the periodic underloading or periodic overloading waveforms. I will give more introduction in the next slides. And after each single underloads or overloads, there's always 200 baseline base load cycles. And this table shows the specimens that I'm going to discuss in this presentation. With these 8 specimens, we can compare the effects of the specimen type solids with hollow specimens. In the solid specimens, of course, the high temperature water environment was surrounding the material. So basically, the initiation was from the outer diameter. For the hollow specimens, the simulated pressurized water reactor environment, they flow into the tube. So the initiation is always from the inner diameter. And then we can also compare the effects of the pressurized water reactor environments and also the effects of the temperature. And then we can compare the effects of the periodic underloading, overloading with the constant amplitude testing. As I mentioned, for the varying amplitude testing, we have either the periodic underloading or periodic overloading. This means after each single cycle of the periodic underloading, we have 200 cycles of the base load. And then in the case of POL, then we have one single periodic overloading followed with 200 base load cycles. And then the next will be one single periodic overloading once more. This slide shows the light optical images and the SEM images of these 8 specimens. And the primary initiation site was marked here. And then we also marked the primary low cycle fatigue propagation deduction and the end of the fatigue testing. In most of the specimens, there is only one primary initiator. And in some cases, there are multiple initiation sites. And in the case of hollow specimens, there are a lot of the initiation sites due to the nature that the initiation occurs in the diameter. And as I mentioned, we have both the constant amplitude testing and also the varying amplitude testing. For the varying amplitude testing, it is possible to track the location, the crack depths where the single underloads or overloads occurs. I will show more examples in the next slides. And for the constant amplitude testing, for evaluation of the fatigue crack growth rate, one needs to evaluate the striation spacing with the crack depths. And in the Ceppänen scale projects, we proposed a common schedule procedure for all the partners to evaluate this striation spacing. And with the common procedure, the scatter of the striation spacing was not limited. So this was done on one specimen, but by 2 different partners. And then the scatter was not limited. For the varying amplitude testing specimens, in Ceppänen scale projects, we propose these VA maps. This means the varying amplitude maps, because they has many advantages over the constant amplitude testing, where we need to evaluate the striation spacing based on the base load striations, because we can easily identify the locations where we have either the periodic underloads or overloads. In this case, it's periodic underloads, and then we can mark, because we know like in each block is 200 baseline striations or baseline cycles, and then we can track from the end of the tests back to the initiation sites. And so we can link very precisely the crack, the fatigue cycle numbers with the crack depths and also the striations, because we know in the spacing between each block is 200 baseline cycles. And another advantage of this method is because usually in the MSC stage, micro small crack range for the constant amplitude testing, it is almost not possible to track these striations in the MSCC range. So like below 300 microns from the initiation side, usually you can't really see striations. But with these VA maps, you can track back to below 50 microns. So it also gives more data at the like near initiation site crack depths. And in this slide, it shows 3 methods for this to calculate the striation spacing on the VA specimens. The method 1, like here is each line represents the underloads, periodic underloads, and then you can evaluate the striation spacing based on multiple blocks. In this case, you have 4 blocks, which is 800 baseline cycles. And method 2 is only measuring the spacing within 1 block. And method 3 is the most typical method, measuring only the base striations. And as we can see here, the method 3 yields the largest scatter compared to the other 2 methods. And also with this base load striation spacing evaluation, you can already evaluate the region which is below 300 microns from the initiation site. And with this, you can only based on the method 1 or 2. So this also once more demonstrates the advantage of using this VMF method. And with the VMFs, in addition to this very precise and robust evaluation of the striation spacing with crack depths, as I mentioned, we can link very precisely the crack depths with the cycle numbers. So one can plot the crack depths with the fatigue cycles. And if you plot it in the linear way or logarithm linear way, one can easily identify if there are multiple initiation sites. In this case, like this specimen actually has 2 primary initiation sites and they merge at certain crack depths. And with these plots, you can identify the crack depths and then these cycle numbers where these 2 crack fronts merged. And this is all impossible with these VA maps. And the other advantage of using these VA maps is that in the logarithm linear plots of the crack depths with cycle numbers, you can do linear extrapolation, and then you will get an estimation of the effective initiator size. And in this plot, it gives an effective initiator size of 15 micron. And if you check the SEM specimen, the near surface, there's the initiator, the diameter is 13.3. So actually it's pretty precise. And the primary initiator is an outside, which is typical in most low cycle fatigue testing specimens in this program. And this slide, I'm aiming to introduce some of the comparisons we did on different test environments. Usually we compare the striation spacing at 1 millimeter from the initiation site, which is considered as a stable stage for the low cycle fatigue testing. And we can see here the pressurized water reactor environments induce like a 10 times or 1 magnitude higher in the fatigue crack growth rate compared to the air tested specimens. And also the cycle numbers where the low cycle fatigue initiation occurred was much earlier, almost also magnitude earlier compared to the air tested specimens. If we take a closer look of the cross sections below the main fatigue crack plane, we can see that in the air tested specimens is mostly form of dislocation cells ahead of homogeneous dislocation cells ahead of the crack tip. And however, in the case of pressurized water tested specimens, there were a lot of shear bands formation, and also below the primary fatigue crack planes, there were a lot of secondary crack formation compared to the air tested specimens. And the strain localization below the fracture surface was much higher in the case of pressurized water air tested specimen in comparison to the air tested specimen. And then we would like to talk about effects of the low cycle fatigue waveform. The periodic underloading waveform, it accelerates the crack growth rate compared to the periodic overloading, and then they were all faster than the constant amplitude testing. The same behavior was for the initiation. So for the periodic underloading and overloading, the low cycle fatigue initiation occurs much earlier compared to the constant amplitude testing. The strain localization below the main fracture surface was also much weaker in the periodic underloading compared to the periodic overloading specimens.
If you can please wrap up. If you can please wrap up, you have 1 minute.
Sorry.
1 minute left.
Oh, okay. And then the effect of the specimen types. For the solid specimens, the initiation was from the outer diameter, and then for all the hollow specimens, we have here 9 initiation sites from the inner diameter. And then the initiation of the fatigue, low cycle fatigue was much earlier in the hollow specimens. However, at a stage with the stable low cycle fatigue testing, the crack growth rate was almost identical for the solid and hollow specimens. So to summarize, the VA maps proposed by Incepha scale, they can provide quite fast and robust estimations, and they can give a precise estimation of the initiator size, exposure to PWR water environments, and the waveforms of periodic underloading, overloading. They decrease the low cycle fatigue behavior. Yeah, that's all. Thank you.